All right, we're going to talk about Euler's method today, which is a method in which we can approximate function values when we can't find the antiderivative and integrate. All right, so I'm going to do a PowerPoint and switch back and forth, and we're going to do slope fields on our calculator, which is pretty cool. All right, so we're going to talk about this guy named Euler, who lived in the 17th century, or in the 1700s, and I wanted to show you this lovely picture of him, and thank goodness gentlemen don't have to wear hats like that anymore. But he was a pretty amazing man. He was nearly blind, or totally blind almost, in his right eye, and still made a number of large contributions to math. And I just thought you should see a picture of him. So what kind of things did he donate to our math language? Well, he was a notation guy, much like Leibniz, and he liked the notation f of x. So he gave us the famous functional notation, f of x. He also gave us the notation for the natural base of e, and the notation for pi, and the notation for I being the imaginary number, or the square root of -1. And believe it or not, he's responsible for summation notation. So he is responsible for a lot of the things that cause math students great distress. And then last but not least, he's also responsible for delta y, which is finite change, as opposed to little dy, which is infinitesimally small amounts of change. Okay, so moving along here, we can find a particular solution from a slope field by looking at it and seeing the families of functions that it could possibly represent. And in looking at the slope field, we can see that maybe if we used tangent lines, we could approximate functions by piecing together little segments to come up with the curve, even if we can't integrate it, okay? And they call that Euler's method. And I kind of look at it as we are jumping on different tangent lines at points so that we can estimate what the function value is. And it'll make more sense when I go through a couple of examples here. So we're going to use Euler's method to graph a solution to an initial value problem. An initial value problem is nothing more than me giving you a particular point that our general solution is going to pass through. So we're going to have to start at the initial condition, which is the point that we're given. And then we're going to have to find the slope at that point. And we're going to use that slope to predict what the change in y is going to be by multiplying dy dx by the change in x. And in effect, if delta x is small enough, it will cancel out with the little dx and give us an approximation for delta y. Creating a new point that we're going to use as an estimate for the function, which would be x plus the small change in y plus comma y plus a small change in x. I'm going to try it again. X plus a small change in x, y plus a small change in y. Easy for me to say. Huh. All right, and then we have the new point, and then we're going to do the delta x iteration one more time to move to a second point that can approximate the curve. All right, and we're going to do it until we get to the point that we want to approximate. All right, so let's do an example here. Let's say I have y equals x squared. I'm going to take a point, the initial condition here, and I'm going to go over a delta x. There it is, delta x. And I'm going to go up with my approximation, delta y, and I'm going to make that approximation by multiplying the slope times delta x. And then my new point is going to be x plus delta x, comma, y plus delta y. And if this delta x is small enough, and I've got this really blown up here, we will be pretty close to the curve here. And this new point would be an estimation for a function value. All right. And like I said, the slope, we would estimate the delta y by using the slope and multiplying it by delta x, and these two in effect would cancel out, approximating delta y. All right, so let's do an example. Because not all things can be integrated, I'm going to choose a simple one that we can, so we can actually show that this process works. Okay, so we're going to start with dy dx equals 2x, and we're going to start at the initial point 0, 1. Okay, so here we go. I like to do a chart, and I'm going to do another example at the end of this presentation here on PowerPoint, an example, and I'll show you how I lay out the chart. But for illustrative purposes, just follow along here. All right, so we're going to have the number of iterations, which I'm going to call n, and we're going to have the initial condition. So I'm going to put 0, 1, and this is before I do any manipulation. And so then I have to figure, there's my point, that's my initial condition. And then I have to find the slope at that point. Well, what is the slope at this point? Well, I'm going to plug in x equals 0 here, and I'm going to get a slope of 0, clearly. And then I'm going to use that slope. I'm going to take the slope, and I'm going to multiply it by the change in x, which is 0.5, because I'm going to go in steps of 0.5. So if I go 0.5 times my slope, I'm going to get 0. So my approximation for delta y, and I really need to change my PowerPoint here to say this is approximately here, but I'll have to do that next time. So my delta y is going to be, in effect, no change. So my new point now, my new point's going to be, I add delta x to x, so on my next iteration, my new point's going to be 0.5, and then I add the delta x, or the new delta y, which is 0 to y, and I get 1. So my new point now is 0.51. So I've moved delta x over and delta y up, and my new point there is at 0.51. Now I'm going to do another iteration, which means I'm going to find the slope, which is 2x, at x equals 0.5. So here we go. That slope is 1, because when you multiply 0.5 times 2, you get 1. And now I'm going to use the slope, which is 1 times delta x here as an approximation for the change in y. And when I do that, I get 1 times delta x, which is 0.5. I get 0.5. And now I know that delta y is going to change y by 0.5. So my new point is going to be, I add 0.5 to x, which would be 1. And then I'm going to add delta y to y, and I'm going to get 1.5. So that's going to be my new point. It's going to be 1.5. So we're going to graph that. There it is, 1.5. And I'm going to do the iteration one more time. So to find the slope at 1, I'm going to take 2 and multiply by 1, and I'm going to get 2. Then I'm going to use that slope to approximate the change in y. So 2 times 0.5 is going to be 1. And then my delta y, when I add 1, will be 2.5. So my new point is going to be delta x plus x, which would be 1.5, 2.5. Okay. And then if I find the slope again at 1.5, which is 3 over 2 times 2x, I get 3. And then I'm going to estimate the change in y by multiplying 3 times delta x, which is 0.5, which is 1.5. And then moving right along, we change to 4. So the new point is going to be 2 and then 4. And if I graph that point, we're going to get an approximation. And if you see that we are getting the shape of a curve that should look familiar to us, Because if I were to find the exact solution, we could separate and integrate, right? I move the dx over and I pull out my magic integral marker. And when I do that, I get y equals x squared plus c. Well, if I solve for c by using 0, 1, I put 1 equals 0 plus c. And I find that c is equal to 1. Oops, I'm going backwards. Sorry, wrong direction. C equals 1. And then my curve is x squared plus 1. And if I graph that, you can see that the tangent lines that I used it's giving us an approximation for x squared plus 1. And you can see that it's an underestimation because tangent lines live below curves when the curves are concave up. So these will be approximations. And that's a pretty decent approximation considering you know, we're using a delta x or a dx as 0.5, which is pretty big. So we call that Euler's method, pretty simply. And clearly, this method would be more accurate if we used a smaller number for dx other than 0.5. And it's going to get less accurate the further you get away from the curve, meaning it's going to be really accurate close to here. But typically what happens is this is going to separate further the further away you get from your initial condition. All right, well, guess what? Your calculator, believe it or not, can do this method. All right, so we're going to do an example. And this is a logistic example, which we'll talk about in the next couple of lessons here. But we're going to type this on the calculator, and we're going to do the slope field first. And yes, you can do slope fields on your calculator. All right, so we're going to change our mode on the calculator. All right, and I'm going to switch back and forth here from the calculator to the PowerPoint. So bear with me. Escape here, and now I'm going to go to my calculator. There it is, and I'm going to zoom in closer here so you guys can see my screen better. All right, and I'm going to type this in. So we're going to change the mode, changing the mode. And I'm going to zoom in a little bit more so you can see what we're doing. Technology is so amazing. All right, so I'm going to change the mode from function mode, as you can tell, to differential equations. So there it is. I'm clicking on that. And I'm going to press enter. And now I'm in differential equations mode. And then we're going to go to see what the y equals looks like. So we're going to go diamond y equals. And you'll notice it looks very different than if we're in function mode. Okay, so in function mode, we just have y1 equals. And in this mode, I would like you to notice that we have a t sub 0 of 5. Now, that's an initial condition I used in the past. Okay, so I'm going to make this a 0. Whoops, whoops, I need to go down here, up here and press enter. I'm sorry, and press 0. All right, and then I'm going to type in my slope field here. And so this is y1 prime, if you can see the little prime there. And so we're going to type in 0.001. And you'll notice that down here, this is a function of t instead of x, because the TI-89 is very good at doing parametrics and seeing things in motion. So your derivatives are going to be dy dx. I mean, instead of dy dx, they're going to be dy dt. So where you see y, we're going to type in y1 because our function is y1 prime. So we're going to type in y1 times, and we've got to use the times in between, parentheses, y1, or I'm sorry, 100 minus y1. Close the parentheses. So I've got, make sure I got that right. I don't have a times here. I need to fix that. Put it, whoop, times in there. Good. All right. Then we press enter. Oops. Let's see. What's my syntax? It doesn't like 0.11. Oh, I don't have another parentheses here, so I need to fix that. Sorry. I got excited there for a moment. All right. There we go. Press enter. There, it likes that a lot better. Okay. And going back to our PowerPoint here. Everybody's got that in there. We type that in, and we're going to do the slope field, mode graph, differential equations, and then we're going to diamond equals, that's where we are. And now we're going to go diamond window. We're going to change the window, and I want you to change the window to those values. So I'm going to escape out of here so we can see both my computer and my calculator. So we're going to go diamond window, and we're going to change things to what we see on the screen here. Focus better here. Oh, there we go. That's much better. All right. So 0, T max, I'm going to put at 150. The T step I want to be 0.2, and that's just when the calculator does the calculations for the slope fields. That's the steps that it'll do in between the x values to do the slopes. Okay, and we're going to set the T plot to 0, the x min to 0, the x max to 300, and the x scale to 10. The y max or y min we're going to make 0, and the y max 150. The scale we're going to put in increments of 10 there, and then these things here I always leave the same. I never change them because they're not, as my PowerPoint says, they're not critical to the operation of looking at the slope fields. Okay, and then the aha moment will arrive here, except I have to go to y equals here and make sure I have my initial condition, which was 10, right? Because we said y1 was 10, or why not? Y original was 10. So go back and put your original condition in there right here. And now we're going to press diamond graph. And lo and behold, we have slope fields on the TI-89. And believe it or not, the calculator is calculating using an approximation method to come up with this curve. Now it's a little bit slow, but it's certainly worth it to see that your calculator can do this. And you can see the logistic graph appearing before your very eyes. And you can see also that it is following the slopes. And it's passing through this initial point, which was 0, 10 over here. And we'll let it finish. But in order to graph a slope field on your calculator, just to refresh here while this is working, you have to change your mode to differential equations mode. And then when you're typing in y equals, you have to remember that your function is going to be defined as y is a function of t. And then you can put your initial condition in your calculator, and your initial condition will be of the form t comma y sub 0, or y t comma y, whatever they give you. And you plug the initial t value. There, my calculator's done. You plug the initial t value into t sub t0 here, and the y value here. So my initial condition was 0, 10. All right. And the graph is still there, which is pretty cool. Okay. So we can do this on the calculator. I'm going to go back to my PowerPoint here. All right. Moving right along. You should have gotten a graph that looks like this. That's for the slope fields. And then, oh, well, I should have done this. I'm sorry, I forgot about that. We're going to change it to Euler's method. And if the t-step is larger, the graph will go faster. If the t-step is smaller, the graph is more accurate, as we mentioned, because that's delta x in effect. All right. And I went ahead because I have a tendency to do that. And that's what the graph looks like. But if we go back, I want to make sure that it's using Euler's method. So let's go back to our calculator. So I'm going to hit escape here. Go back to the calculator, and While you're in the graph, you're going to hit the diamond, such that bar, and you're going to see something pop up that says graph formats, which we wanted in rectangular form, and it talks about the grid, the axes, the leading cursor, the label, the solution method. Now, the solution method is, there are going to be three methods that this calculator can do. This calculator can do the Runge-Kutta method, which is the RK method, which you see there. And then if you arrow over, you'll see that you have Euler's method. And we're going to click on Euler's and press enter and save. And then it's going to graph it again. And you'll see that Euler's is a little bit faster than the Runge-Kutta method, because the Runge-Kutta method is a lot more involved and is more accurate, but takes the calculator a little bit more time to come up with the solution. Now, we don't have the equation for this, but we certainly have what the graph looks like, which is really cool, using the approximation method of Euler's. And they're doing the t-step. This calculator is doing the t-step where it's doing the delta x over and up delta y, using that very approximation method that I went over just a second ago, where you have x and y and you use the slope at that point to approximate the delta y, and then add that to delta y, and you come up with a new point. And that is Euler's method visually right there. Okay. All right, back to my PowerPoint here. All right, while it's still displaying the graph, we change it to Euler's method, which we did, and we saw that it was faster. And that's what your graph should look like. All right, now let's say we want another initial value, a different one. So what are we going to do? We can go F8, and we can either enter the new point, or we can just use the move the cursor. All right, so I'm going to zip out of here, and let's do that on the calculator. All right, so we're going to say, all right, let's hit F8, which is up here. Do you see it's above the graph key? So we're going to go second, F8, and it says initial conditions. And let's say we want one that passes through t equals, oh wait, did I hear something from the back there? Let's say it's going to pass through t equals 0. Did I hear something greater than 10? Or maybe something greater than 100? Okay, so we're going to say t equals 0. And then we're going to say y equals, let's see what happens if I choose a point that's above here, because that would be interesting, don't you think? So what is this line here? This equation, this slope field, we said was 0.001y times 100 minus y. So the slope is 0 at y equals 0 and at y equals 100. So let's say our initial condition is, instead of 75, something greater than 100, like 120. Well, guess what? Our calculator will graph the solution for the particular solution that passes through the point 0, 120. And you see, if your initial condition is up here, your graph is going to be asymptotic coming from the top, which is pretty cool. All right. And it's still busy because it's still working all the way down here. All right. It's while it's thinking. So I just typed in another initial condition, but do you see how we could use either the cursor as well? I'll do that in just a second. Think. Anything interesting, other things I can think about this? Okay, it's done. All right, and if you notice on the PowerPoint, it says you can also investigate the curve by using F3. So I'm going to use F3 here, and I can use the trace button, and I can find out what the values are on this function when t equals certain numbers, which is pretty cool. Let's see what happens as I get further along. See, I'm way down low here. And see, it's just following the delta y, delta x. You see as I'm pressing that? Trace, I'm just going to the right here. All right, so you can use the trace. And that's the F3 up here, trace. All right, going back to the PowerPoint, let's see what we got. All right. We already did all that. All right, so let's go back to our original calculation. Okay, so what do we have to do? We have to go to diamond y equals, and let's change that. And we're going to change the window because we know all about that curve and what it looks like. And then we're going to do the such that bar so that we don't see the slope fields, okay? So getting out of this, we're going to see the calculator here. So I'm going to go to diamond y equals, and I'm going to change my initial condition now to 0, 1. So that's still 0. And then this is, I have to click down on this and hit 1. Yep, and so my initial condition is 0, 1. And I'm going to clear this out. And since this is a function of time now, instead of x, I'm going to type in dy dx, which is y prime of t. We're going to go 2 times t. All right, and there it is. And then I'm going to go to my window, diamond window, and change my my t max is going to be a whole lot less than 150. And let's go to 10 because that's the x. And then we'll make our t step 0.5, right? Because in our initial problem that we did, we used the delta x was 0.5. And I'm going to leave the t plot starting at 0, and the minimum was 0, and we'll say the maximum instead of 300 is 10. And we'll say the y min is 10, and the y max will make 5. And remember, we leave all of these things alone. I'm going to make the scale on the x1, and let's make the scale on the y, the x1 and the y1. So 0 to 5 in increments of 1. And we'll leave the e step and all of that stuff the same. And then we're going to go diamond, such that, and we're going to go down to the fields, and we're going to turn off the slope fields. Okay, so that means the slope fields aren't going to show on our graph. You're like, oh, but I really like the slope fields, but we'll play around with that in just a second. Okay, so now we're going to go diamond graph and be amazed that that is the Euler's method right there. That was what you saw earlier on the PowerPoint. Okay, and what's really, really cool about this is that we can now go to diamond table set, and I'm going to start my table at 0. And what was delta x? Delta x was 0.5. So I'm going to go 0.5 here. Enter. And now let's go diamond table. And there's the Euler's method, right? We went 0, 1, and we went 0.51, 1.5, 1.5, 2.5, and 2, 4, which is really cool because that's the Euler's method that we used earlier. So I'm going to go back to the graph, and I'm going to hit F3 trace. And what happens if there's my 0.51, then I went 1, 1.5, and then I went over delta x up delta y to 2.5, and then the last one was 2, 4. And you could keep going if you wanted using this same Euler's method. All right, that's pretty cool. Now let me finish this so we can do some examples. All right, so we can reproduce our first graph. We did this, we did this, we did this, and then we hit graph, boom. And then I did the trace part second, but then I went back to the table set, changed the delta table to 0.5 because that was our delta y or delta x. And then you saw that that was our Euler's method with the steps that we had. Our book refers to an improved Euler's method, and in college you'll probably hear that as the modified Euler's method, and you don't need to know that. The AP exam only covers Euler's method, not the modified or improved Euler's method or the Runge-Kutta method. When you take differential equations in college, you will talk about both of these other two methods. And what's good to know is that your calculator can do both, which is pretty cool. All right. So that is Euler's method on the calculator, slope fields on your calculator. And I'm going to make, whoops, I'm going to clear this out, second quit. And I'm going to go to the graph. And I'm going to go such that, or diamond such that, I'm sorry, diamond such that, and I'm going to turn my slope fields back on because I really like to have my slope fields on. Okay, there it is. And it's going to graph it, the Euler's method with the slope field. So you can see that it actually does follow the slopes. All right. So let's do some examples. And I'm going to make this bigger. And I'm going to make this bigger so that we can see more of my paper when we do an example. Logistics, right, of make this really tall so we can really see more of my paper. There we go. And focus. All right, so let's do an example by hand. All right, I have a blank one of these sheets on Moodle or in your hands, maybe if you came and got it earlier or after school yesterday. And this is what you would do to do Euler's method by hand. And I have what the solution looks like down here, but we're going to do Euler's method by hand. So this question says, use Euler's method with delta x equal 0.5 to approximate f of 3.5, where f satisfies the initial value problem. And this says f prime of x equals x, and f of 2 equals 2. All right, so what this problem is telling us is that dy dx is equal to x, and that my initial condition is 2, 2. So this is where I'm starting at 2, 2, and I want to approximate f of 3.5, and I want to go from 2 to 3.5 using steps of 0.5. All right, so this is how I set up my table when I'm doing Euler's method. I go xy, which is my original point, and then I go delta x, and then I say dy dx, because I'm going to use dy dx to approximate what delta y is by taking dy dx and multiplying it by delta x. And then my new point is going to be x plus delta x, comma, y plus delta y. All right, and I'm starting at 2, 2, so I'm going to put 2, 2 here. And delta x every time is equal to 0.5. So I'm going to put 0.5 here, which is also 1/2, which is nice. All right, so I'm going to find dy dx, which is equal to x here, when I'm at this point. So what is the slope at 2, 2? Well, the slope at 2, 2 is 2. So delta x and delta x and dy dx are going to be used, I'll multiply them together here, dy dx times delta x, to approximate what delta y is going to be. So if I multiply these two together, I get 1. And my new point is going to be x plus delta x. Well, that'll be 2.5, comma, and then I take y and I add delta y to it. And so this is going to be 2 plus delta y, which is 2 plus 1, which is 3. So my new point, I have moved from 2, 2 to 2.5, 3 using Euler's method of approximation. So now I take this point and I bring it back over here and say, okay, well, that's going to be 2.5, 3 because I'm going to do this until I get to 3.5. All right, so let's do that. So I know that delta x is still going to be 0.5 because I'm going in increments of 0.5. And then the slope here is going to be 2.5 because it's just whatever x is, 2.5. And when I multiply them together, these two together, x and dy dx, to get the approximation for delta y, I'm going to get 1.25. And then I have a new point because I'm going to move over to 3 because x plus delta x is 3. And then 3 plus delta y is going to be 4.25, which gives me the new point, moving that over here, of 3, 4.25. All right, so now I'm going to do the same iteration because I have to end at 3.5. Okay, so delta x is still 0.5. The slope is going to be 3 because it's whatever x is. And if I multiply 3 times 0.5, I get 1.5. Coming up with my new point, which is 3.5, comma, and then I add 4.25 plus 1.5, which gives me 5.75. And so now I can say that f of 3.5 by Euler's method is approximately 5.75. So this is kind of my terminating point. And so this is Euler's method. And I took the liberty of doing this on WinPlot. And it says solve the initial value equation and use your solution to find the exact value of 3.5. All right. So if I were to solve this differential equation, and I don't have a lot of space here, so I'm going to do it over here. So I say dy dx equals x. If I separate and integrate, I say dy equals x dx. And I'm going to pull out my magic integral marker. There we go. And we get y equals x squared over 2 plus c. And using my initial condition, which was 2, 2, I can say that 2 equals, that would be 2 squared, which is 4, over 2, which is 2, plus c. So c equals 0. So my function is going to be f of x equals x squared over 2. And if I were to find out what f of 3.5 is, that's going to be 3.5 squared over 2. Let's do that. We get 3.5 squared divided by 2. And the calculator says, well, that's a whopping 6.125. All right, so this is the actual value of f of 3. And because this curve, x squared over 2, is concave up, our estimation is an underestimation, and we expected that. All right. Now, I'm going to use our calculator here to show you that our Euler's method was correct. Okay, so how do we do that? Well, we go back to y equals, and our differential equation was t instead of, whoops, I have to press enter, t instead of 2t. And my initial condition was 2, 2. So let's put that there, 2, 2. And let's look at what that slope field looks like. Let me see what the window. Let's look at the window. Then it's going to go from the T max is, I think that's fine because we're going from 2 to 3.5, so we're okay there. The step is 0.5. Let's leave the plot at 0.2. And let's x min is 0. That's fine. X max is fine because you know, in the xy, I think we'll be okay. And then let's make this bigger. Let's make this 10. And the increments are okay. I'm all right with that. And we leave all these alone. And then we're going to go diamond graph. And so there is our curve on our calculator. And there's 2, 2, and there is our curve using Euler's method. Now, we can use the trace button, or we can go to the table. I like to go to the table set because then it kind of shows you that this works. So let's go diamond table set. And where do we want our table to start? We want our table to start at 2, because that's what our initial value was. Focusing again, sorry. So we're going to put 2 there. And I want my table to be in increments of 0.5. And then I want to press enter. And then I'm going to go look at the table, second table. And there we go. See, we have our initial point, which was 2, 2, and then we hop to 2.53, and then we hop to 3, 4.25, and at 3.5, the Euler's method is going to give us 5.75, which is pretty cool. All right, so our calculator actually does verify that. Pretty nifty. Okay. All right, so that's an example by hand. And most of these questions are going to be on the non-calculator section. And they'll give you reasonable numbers like this most of the time. But all right, so let's have some fun and do some AP calculus questions that were on the last 2 AP exams. So I'm going to quit out of here. And both of these are going to be non-calculator and are going to be in this packet that I'm going to post online called, Separation Anxiety, No Way, Differential Equations AP Style. And if you'll notice that I'm going to do the 2017, which, yes, it is the potato problem, but I'm going to do that one second. And I'm going to do the 2016 problem first because this problem has an Euler's method section in it. And I think that is pertinent to what we were doing just now. All right, so I'm going to minimize this so that we can see my work and we can see the problem 2016 on the other side of my screen here, okay? All right, so let the fun begin here. So this is going to be BC 2016 number 4, free response number 4. All right, so the question says find the second derivative in terms of x and y. So this would be part A. If I know the first derivative is equal to x squared minus 1/2 y, I can take the derivative of this implicitly with respect to x, and I'm going to get 2x minus 1/2. And what's the derivative of y implicitly? Well, that's dy dx. But what is dy dx? We're going to have to substitute in for this. And dy dx is nothing but this. So I can rewrite this as 2x minus 1/2 times x squared minus 1/2 y. And we can simplify that. And that'll be 2x minus x squared over 2 plus 1/4 y. And that's the second derivative with respect to x. That's part A. Nice. All right, part B states, let y equal the particular solution to the given differential equation whose graph passes through the point -2, 8. Does the graph have a minimum, maximum, or neither at the point -2, 8? All right, well, in order to know about minimums and maximums, it has to be a critical point. So I'm going to say -2, 8 is my point. And I'm going to find out what the derivative equals, which is x squared minus 1/2 y, when x equals -2 and y equals 8. And let's see, when we plug that in, we're going to get 4 minus, well, 1/2 of 8 is 4, which is 0. Therefore, it's a critical point. So this is a critical point. And then I'm going to try out the second derivative, because if this is the second derivative test, by the way, if I know what the second derivative value is, then I'll know if it's concave up and concave or concave down. So let's figure out what the second derivative test is. That's going to equal 2x minus x squared over 2 plus 1/4 y from above here, such that x equals -2, y equals 8. Now, I could check the slopes on either side of it using this, but this is a pretty easy test because we have the numbers here. All right, so let's plug in the values and see what we get. We get -4, 8. I'm sorry, we're going to use 8 last. So this is going to be -2 here. Squared is 4. 4 over 2 is 2. So this will be -2. And then if I plug 8 in here, I get 8 over 4, which is +2. So these cancel, and I get -4, which is less than 0. All right, so what does that tell us? Well, that tells us that f of x has a maximum at -2, 8, since dy dx is equal to 0, and the second derivative with respect to x is less than 0, meaning it's concave down, and the only place for it to have a 0 slope is on top, which makes that a maximum. And this is the second derivative test. So if it's a critical point and it has concavity that is down, then the only place the tangent line can be is on top, and therefore it's a maximum. So this would be our answer. All right. So far, so good. Part C says let y equal g of x be a particular solution to the differential equation with g of -1 equals 2. All right, we're not ready yet to do part C, so we're going to have to hold off on part C because we have to use something called L'Hopital's rule, which I'll get to in a little bit. So we'll come back to part C when we hit L'Hopital's rule. So we're just going to do part D. All right, part D says let y equals h of x. So we're looking for y equals h of x be a particular solution to the differential equation with h of 0 equaling 2. So h of 0 equals 2. Sorry, let's write this better. Which means our initial condition is what? 0, 2. Use Euler's method starting at x equals 0 with 2 steps of equal size to approximate h of 1. So we want to know what h of 1 is approximately. So they want us to use 2 steps between 0 and 1. So what does that imply that delta x has to be? Yes, I hear it from the back of the room. 0.5, you're right. It has to be 0.5. So we're going to set up our Euler's method table, and we're going to have our xy point that we start with, and then delta x column, and then we approximate using the slope. So I'm going to put a slope column, and then delta y is approximately the slope, which is dy dx, times delta x. And then we come up with our new point, which would be x plus delta x, comma y plus delta y. All right. So now I'm starting with 0, 2. And delta x is 0.5. And the slope is going to be dy dx, which we already know, dy dx, I didn't put that down here again, is x squared minus 1/2 y. All right, so our slope at 0, 2 is going to be 0 minus 1. So our slope is not -1. And then delta y is going to be approximated by multiplying these two together. And so we get -0.5. So our new point is going to be x plus delta x, which will be 0 plus 0.5, which is 0.5. And then I'm going to add delta y to y, which means I'm going down in the y direction, so it would be 1.5. And that's my new point, and I'm going to take that new point and move it over here, because we're not quite at 1, so it'll be 0.5, and then 1.5. And then delta x is still 5, because we're going in increments of 0.5. And then dy dx, I'm going to use this point to find the slope. All right, which means 0.5 squared is, or 1/2 squared is, I'm going to have to do some calculations here. 1/2 squared is 1/4 minus 1/2 times y here is 3/2. Okay, so that's going to be 1/4 minus 3/4, which is negative 0.5, right? Or negative 1/2, because that's negative 2/4. All right, and when I multiply those together, I get negative 0.25, which is negative 1/4. And now my final point is going to be, I'm going to add delta x to x, which gives us 1, comma, and then I'm going to subtract 0.25 from 1.5 and get 1.25. So we can say then h of 1 is approximately 1.25. H of 1 is approximately 1.25 using Euler's method. And they aren't asking us anything about whether it's concave up or concave down. So we're done with that. All right. And so we can check the scoring guidelines and see how many points we would have gotten for each one of these. Make it a little bit smaller. So you get 2 points for part A. That's nice. And you get 2 points for your conclusion that it's a maximum, and your justification, which we used the second derivative test, and they did too in the scoring guide over here. And then this, like I said, part C we're not ready to do yet. And then part D, let's see here. You get 1 point for Euler's method and 1 point for the approximation. And so Euler's method, I like to show in a table. Clearly they didn't show it in a table. And the approximation is equal to h of 1 is 5/4, which is 1.25. So ours is equivalent. So we got 6 out of 9, and we would have gotten 3 more if we'd known how to do L'Hopital's rule, which we don't know how to do yet. All right. One last problem and we're done for the day. And that's going to be our lovely potato problem. All right, so let's do the potato problem, which caused a lot of AP kids and calculus kids some consternation on the AP exam in May of 2017. So let's make this not very difficult. All right, so at time equals t, a boiled potato is taken from a pot on a stove and left to cool in a kitchen. The internal temperature of a potato is 91 degrees Celsius at time equals 0. So they're telling us something there, and I like to write down a lot of times what they're telling us. They're telling us that the initial condition is 0, 91. All right, and the internal temperature of the potato is greater than 27 degrees Celsius for all time t, greater than 0. The internal temperature of the potato at time t can be modeled by the function h that satisfies the differential equation. So they're giving us a differential equation. So here we go, dh dt is equal to negative 1/4 h minus 27, where h of t is measured in degrees Celsius and h of 0, well, there it is, they gave it to us anyway, is equal to 91. All right, so part A says, I guess they named it H for hot potato. That's pretty funny. All right, write an equation for the tangent line to the graph of H at t equals 0. So in order to write an equation of the tangent line, I need a point and a slope. So at t equals 0, I have a point, 0, 91. All right, and I need a slope. So I need dh dt at t equals 0. Well, I don't have a place to put t, but I have a place to put h. So that's going to equal negative 1/4 times 91 minus 27. Now, this is question number 4 on the BC exam, which means there is no calculator. So we have to do this in our head. So 91 minus 27, 8 carry the 1. This is 4. This is 64. Sorry, I have to do that sometimes. 1/4, negative 1/4 times 64, which is equal to negative 16. So that's the slope. All right, so the slope is 16, the tangent line, to h of t at t equals 0 is going to be y minus 91 equals negative 16 times t minus 0. So that's the tangent line, and I would just leave it right like that. And then I go back to the question to see if I've answered it all. It says, write an equation of the tangent line to the graph at t equals 0. Boom. Use this equation to approximate the internal temperature of the potato at t equals 3. So I'm going to say h of 3 is approximately negative 16 times 3 minus 0, and I'm going to bring the 91 over, plus 91. So that's going to be negative 16 times 3 plus 91. And that's approximately negative 48 plus 91, h of 3. Now, this is going to be in what unit? The temperature of the potato. So this is degrees Celsius. And theoretically, you can leave it like this. But what I want to do is find the exact answer. So this is 91 minus 48. 8, this is going to be 3, and then this is going to be 4. So this is going to be approximately 43 degrees Celsius using the tangent line as our approximation. So that's part A. Lots of work for part A. All right, part B. Use the second derivative to determine whether your answer in part A is an underestimate or an overestimate. Okay, so remembering that if tangent lines are above, then it's an overestimation. If tangent lines are below, that's going to be an underestimation. So we need to know its concavity. So I need to take the second derivative of h with respect to t. So in order to do that, I have to take the derivative of this implicitly up here, because this is not a function of t, it's a function of h, which is like the y up here. So taking the derivative, I'm going to say negative 1/4 times the derivative of this, which is just dh dt. But do I know what dh dt is? Well, yes. So I can substitute in, this is equal to negative 1/4 times dh dt, which is negative 1/4 times h minus 27. Let's write it properly. Which is 1/16 times h minus 27. And I'm going to have to figure out whether this is an overestimation or an underestimation. So I have to figure out what this is when t equals 0 and h equals 91, because I'll know where the tangent line is, so whether it's above or below. So this is going to equal 1/16 times 91 minus 27, which I found out above was 64. So this is going to be equal to 4, which is greater than 0. So I can say that the tangent line approximation for h of 3 is an underestimation since the second derivative is greater than 0 and h of t is concave up. And I like to make the statement and the tangent line is below, because I'm expressing at least that I know that the tangent line is below the curve. Never hurts to show them what you're doing, okay? So there we go, that's part B. And then part C says an alternate model for the internal temperature. Part C, an alternate model for the internal temperature of the potato at time equals t is the function g that satisfies the differential equation. So dg dt is equal to negative g minus 27 to the 2/3, where g of t is measured in degrees Celsius and g of 0 is 91. So they're giving us the same initial condition. So g of 0 is equal to 91. All right, so we're going to find an expression for g of t, which means we are going to separate and integrate to solve this differential equation. So we're going to leave the negative over here. So we're going to say dg over g, oops, sorry, let's write that so it doesn't look like a 6. G minus 27 to the 2/3 equals negative dt. And I'm going to pull out the magic integral marker now. And to integrate this, I'm going to make this a negative exponent here. So we're going to go g minus 27 to the negative 2/3 dg is equal to negative integral dt. And I'm going to use u substitution here. But if I use u substitution, du is going to be equal to dg. So this is really going to be g minus 27 to the raised to the power 1 is going to be to the 1/3 divided by 1/3 means I'm going to multiply by 3 equals negative t plus c. All right, now I've got to get g all by itself. So I'm going to divide everything by 3. So we're going to get g minus 27 to the 1/3 equals negative t over 3 plus c, because if I divide c by 3, that's still a constant. All right, and now I'm going to cube both sides. So I'm going to get g minus 27 equals negative t over 3 plus c, quantity cubed. And now I'm going to say that g of t is equal to negative t over 3 plus c raised to the 3rd plus 27. So this is my general solution. But the question is asking for finding an expression for g of t. So they want the particular solution. So using the initial condition that we have, 0, 91, I'm going to say that 91 is equal to, well, when you plug 0 in here, t over 3 is 0. So we get c cubed plus 27. And if I subtract 91 from 7, I keep doing that. 91 minus 27 is 64 equals c cubed. So c equals 4. So my expression for g of t is going to be negative t over 3 plus 4 raised to the 3rd plus 27. So there's my expression for g of t using my initial condition. And I want g of 3. Well, g of 3 is going to equal, this is going to be negative 1 plus 4, which would be 3 cubed, which is 27, plus 27, which is 54 degrees. So g of 3 is equal to 54 degrees. All right, well, so that's the scary potato problem. not too scary after all. All right, so that's the end of our Euler's method and solving a little bit of AP calculus problems video of the day. Have a great day.